Welcome to this topic on AI HPC principles. We will first go through the overview, then we'll talk about two very important laws, Amdahl's law and Gustafson's law, and then we'll talk about the roofline models, and lastly we'll conclude with the interconnections for high performance computing or ICN. Well, first the overview. So in this particular section, our main concern is about what are some of the limitations to the speed up factor, or how much faster the computation will increase when you increase the number of processors. Now, it may be non-obvious for people who are not familiar with this field. So, for example, if you have a group of data scientists who may ask themselves if a very large random forest takes a huge data set, and it takes about 100 minutes to train it on one single computer or one single CPU. Now, if these data scientists then ask themselves, does it mean that if they actually train this with parallel jobs, right, instead of having just one single CPU, and they actually try to do the same training with the large random forest with 100 CPUs, does this mean that 100 minutes that they used to take will now be cut down to just 1 minute, because each CPU will take 1/100th of the job? So if the original time was 100 minutes, then when you divide it by 100, you just get 1 minute. Or if they were to scale this even further, and if they have 1000 CPUs, does this mean that they can cut down the training time to 1/10th of a minute, or just 60 seconds or 6 seconds? But unfortunately, this is actually not going to happen, and the actual performance that these data scientists will get when they actually increase the number of CPUs is not going to be linear, right? Because there are some limiting factors besides just the CPU resource being required uh, to run that random forest training. So the speed up or the decrease in time that they expect would not actually be proportional to the number of CPUs as they would have wanted it to be. As I mentioned, this is because there are actually other limiting factors and we're going to take a look at some of these laws that govern this in the surrounding in the next few sections. So in the following sections, we hope to answer the following questions. Number one, what is Amdahl's law, and what are its implications as far as training for AI and HPC is concerned? And secondly, what is Gustafson's law? How does it improve our understanding from Amdahl's law? Then we will take a look at what are roofline models. How does it help us to visualize what's happening in the computer system? And then we're going to take a look at how the interconnection infrastructure in the AI HPC computer affect the overall performance of the system. And lastly, we're going to take a look at also some of the common HPC interconnections that have been used for some of the fastest computers available, the top 500 computers available in the world today. So we'll kick off with Amdahl's law. So Amdahl's law is often used in parallel computing to predict what is the theoretical speedup when you use multiple processors. So for example, if a program just needs 20 hours to complete using one single CPU or one single thread, does that and but there's one portion of this program that actually cannot be parallelized. That means it will always only run on one single CPU, and only the remaining 19 hours or 0.95% of the execution time can be parallelized. Now, if there's this limiting factor, there's a constraint on how much can be parallelized, how much speed up is actually possible. And as you can see from this graph, the first part of the program is basically pretty linear. It will increase as the number of CPUs increases, but then there is this tapering effect as the number of CPU increases, and there's actually a limiting factor that it sort of hits the roof and it cannot actually increase beyond a certain level of number of flops or operations per second. Right, so you can see that irregardless of the uh, number of process the number amount that's parallelized, there's always this limiting factor. And the other trend that you will notice that actually if the amount of operation that can be parallelized is only 50%, the roof or the ceiling is much lower than if the percentage that can be parallelized is 95%. So in other words, actually the limiting factor is how much serial portion of the program is there. If there's a high amount of serial portion that cannot be parallelized, then there's an inherent limiting factor um, in the top performance of the system. That means it does beyond a certain number of CPUs, it will just saturate, and there's no way that you can feed these CPUs with the enough work to do, such that the overall performance will just not increase beyond a certain limit. This is basically what Amdahl's law tells us, that beyond a certain limit, if you have not 100% but just 90 over percent of the execution time that can be parallelized, no matter how many additional CPUs or threads you devote to this execution, there is a limiting factor. In other words, the minimum execution time can never be less than 1 hour, which is actually happens to be the amount of time that cannot be parallelized. So that 1 hour that can only run on one CPU, you can never go below that, since increasing the number of CPUs will just parallelize the rest of the 19 hours, but the 1 hour will always be 1 hour. It cannot be reduced by trying to execute it on multiple processors. So in terms of the formula for the Amdahl's law, if we have P as a proportion of the system that can be parallelized, then, well, 1 minus P, which is the remaining fraction, is the proportion that must remain 0. As we said before, this is actually the limiting factor in Amdahl's law. And then the maximum speed up, or Sn, that we can achieve with n processors is actually given by this formula: 1 divided by the sum of S, which is 1 minus P, plus the total amount that can be parallelized divided by the number of processors. So you can see that actually as n tends towards infinity, when you have a huge number of processors, this term P divided by n goes down to 0, which means that the overall speed up, that roof, is affected by 1 over S, or 1 over 1 minus P. So this gives us a theoretical limit as to how much of the system uh, can be speeded up, irregardless of the number of processors. So in other words, the speed up is actually limited by the total time needed for the serial part, the 1 minus P part of the program. Next up, we're going to take a look at Gustafson's law. So this law is actually a refinement of what we see in Amdahl's law, where we had a linear increase in the performance or speed up only at the front, in the initial during the initial period of increasing number of processors, and then actually hits the limiting factor. So Gustafson actually tries to address some of the shortcomings, because he noticed that actually Amdahl's law is flawed in the sense that it makes a fundamental assumption that as we have more CPUs available, the size of the job is always the same. It doesn't actually increase. So it's a fixed problem size. And because of this fixed problem size, the non-parallelizable portion, the serial portion, becomes a limiting factor. Gustafson assumes that actually this may not be true in all cases, and that for many problems, instead of trying to solve the problem in a smaller amount of time, we actually want to have a better or more accurate answer. In other words, the job size may not be fixed. It may actually increase when we have more resources available, right? So Gustafson actually, he proposes that programmers actually tend to get better results or more accurate results with higher computing power, rather than just keep the job size constant. So in other words, with this additional factor that the job size or the problem size actually increases, the speed up factor can be actually made more linear. And in Gustafson's law, the speed up is actually same formula. Speed up Sn is actually equals to S, the serializable portion, plus the parallelizable portion times the number of processors. So if we simplify it, we find that actually, again, it is limited by the number of processors. But now we can also increase, when n increases, P just determines how much it scales up, right? So we can actually get a almost linear As you can see from the graph here, there's no longer the roof, right? It just goes up and up and up as you add more processors. And we can conclude that basically the proportion that can be parallelized actually gives us the slope of this function. How much increase in flops do we get as the number of processors n increases? So this is, in summary, is what Gustafson's law is, right? So it's a refinement of Amdahl's law, where we remove the constraint of having a fixed problem size. What are some of its implications in our understanding? So first of all, Gustafson's law now gives us a linear model between the processor count n and the speed up factor s. So in other words, the slope is just purely dependent on p, the amount that can be parallelized, and there's no limit as we increase the number of n, so we can keep getting better and better performance. However, this will only be true if the problem size actually increases. So the higher proportion the program of the program that can make parallel, or p, the steeper the slope. In other words, it will speed up faster if we can parallelize it better. And currently, the speed up basically scales linearly with p rather than exponentially as in Amdahl's law. The impact of this Gustafson's law is really to shift the research goal from just trying to reduce the time for execution and keeping the the problem size constant, because we are not going to achieve a certain level of speed up as limited by Amdahl's law. So instead of trying to just keep the time lower and lower in terms of the total execution time, instead we should use the more resources that we get to actually get better results. So we can actually do more with more processors, but the amount of time that we will take will still be the same. So this is the implication for Gustafson's law. So if you go back to the problem that we had earlier about the data scientists trying to train a very large random forest with a huge data set, they find that actually with one single CPU, they're not able to speed it up very much if they actually increase the number of processors. So maybe the amount that can be parallelized is 90% in the random forest, so that remaining 10% they can never speed up. So they will increase the number of processors and try to reduce the time using Amdahl's law to mitigate against that 10% that cannot be serialized. But beyond that, actually, they should not try to increase it further, because adding more processors will not reduce the time anymore. And Gustafson's law suggests to these data scientists that once they have already attempted to reduce the execution time using Amdahl's law, the next thing that you should look at is how they can improve if they have still more processors available, like that 1,000 processors, right? Instead of trying to reduce the time, maybe the more logical goal is maybe to increase the size of the tree, right? Beyond maybe 100 estimators, can they use 200 or 500 estimators in order to get a better result? So this is basically how the two laws are interacting in a problem. So the first law just tells us that yes, we can get some speed up. Amdahl's law just tells us that we can get some speed up, but we cannot go beyond a certain limit. And Gustafson's law basically suggests to us that once we have already tried to speed up the program, the additional processors or resources that we have should not go into trying to speed it up further, but to try to get better results, okay, with the additional resource. Next, we're going to take a look at roofline models and how they help us to visualize what's happening in the computer system. So the roofline model basically is a visualization, a technique that allows us to give an estimate of the performance of the system. Is it actually bound by CPU resources or by the memory bandwidth that's available in the system? So typically, the model has two axes that are in log scale. On the lower axis or the horizontal axis, we have what we call the arithmetic or operational intensity, which is basically how many operations can be performed divided by the total amount of transfer of information, or bytes. So it's the flops per byte axis, the arithmetic intensity. So as you have more operations per byte. It means basically you are also transferring more data across the interconnect within the system. So there's a certain memory bandwidth that you exercise. And on the vertical axis, we have the performance in terms of flops or floating point operations per second. This is a typical measure. Of course, we can use other measures, but in data science, at least, flops or arithmetic operations is a typical limiting factor. So here we see that the performance is measured in terms of gigaflops. Again, this is on a log scale. So you can see here in the roofline model, the initial part, this diagonal here is actually it actually calculates the limiting factor or the bound based on the memory bandwidth. How fast can the system transfer data from the RAM to the CPU, etc. Okay, it's actually the bandwidth of memory transfer within the system. Now, if the system is actually disputed, as we can see later on, then the memory bandwidth is not only on the computer bus, but also the interconnection between the different systems as well. Okay, so this is the first part. And then the other part is actually the performance bound based on the peak CPU. I mean, how fast the CPU can actually run. Okay, this is actually the maximum speed of the CPU. And if you have more CPUs available, of course, the number of flops would just go up, right? So this is based on the total number of processors you have available as well. So you can see that you will typically have this reach point, that is the corner point, where the limiting factor switches from just the memory bandwidth to the peak performance of the total number of CPUs that you have. So this is the example of a roofline model in the basic form. So you can find that different applications could be well within the total performance of the system, because these bounds, they actually are the limit. You cannot have a process or a job that's running faster than this limit. In other words, they are like a speed limit. You cannot go beyond it. So here's this more detailed diagram. So I, as I said, is the arithmetic intensity, which is the work divided by the total number of bytes being transferred. So it's measured in flops per byte. And as you go towards the right, actually you're doing more work, but you're also transferring more data at the same time. Okay, so there's a if we in the initial part, actually we are not running the CPU to the ground, so actually the maximum performance is typically limited by this the slope of this line. Okay, because I is the axis, so beta, the B factor, is actually the memory bandwidth limiting factor. Okay, the peak bandwidth. So this is actually a diagonal line, because it basically scales linearly until it reaches the maximum speed of the CPU, the pi factor here. So once it reaches the total maximum number of flops that all the CPUs can run, it will also hit another performance limit. But you can see that actually now the limiting factor will no longer be the memory bandwidth, right? But actually the total amount of flops that we are running. So there's two regions here. If that's quite critical, and that's actually pi divided by the pi divided by the beta factor, okay, which is actually corresponding to this reach point at the corner here. So if the values of I is below this pi divided by beta, then the program is basically in the memory bounds. In other words, it's not going to be able to run any faster, not because we do not have enough CPU resources, but because the memory bandwidth is not sufficient to make it run any faster. Okay, so once and then the other bound would be what we call the compute bound. That means we cannot run it faster because we just do not have enough CPUs. Okay, so if you remember from one of the earlier examples that we had in another topic, this memory bound and compute bound will also affect the training of machine learning models, but it's reflected in the hardware itself. This optimized, these memory bounds and compute bound, they are not for the software or the training process, but they are actually the maximum performance of the hardware architecture itself, the computer hardware itself. So again, the computer hardware has also a compute bound and a memory bound. So this is what I mentioned just now. If it's below pi divided by beta, it is the memory bound by the computer hardware, and if it's above this, it's actually compute bound. Next, we're going to take a look at some of the interconnects for the high performance computing. What actually affects the beta factor, the memory bandwidth, if we have a distributed computer system. So to understand why this is actually a factor, the interconnect, we need to take a look at the evolution of high performance computing. The first top uh, 500 computer, the best computer, initial versions of this were basically one giant computer, right, or vector computer, which can do many operations per second, and the speed of the memory transfer is basically limited to the computer bus itself within the computer. But as time went on, actually the fastest computers or supercomputer around, and you can take a look at the top 500 top systems, they went from a single computer to basically a network of computers, right? So so there's a smaller network, then it went down to even bigger one, the Tianhe here, and then the Fugaku, currently one of the largest and fastest supercomputers. You can see that the size of the network basically has increased from just a few racks to basically a warehouse, right, or a very big warehouse of supercomputers. So with each successive generation, the number of processors increases, but also the amount of interconnection you need between the processors also increases. So the interconnect actually becomes a ever critical performance bottleneck because of this scaling with distributed computing. So we're going to take a look at two important factors that affect the memory bandwidth, right? So how much you can transfer. Number one is what we call the bandwidth, is how much data transfer or the size of the data that you can move per second. And the other factor is what we call latency, which is a measure of the delay of in the data between two nodes. Now in HPC, we often need to move data in the size of gigabytes per second through the interconnection. So if the data is not going to be moved fast enough, then some of the processors will be starved of data, and it's basically going to be waiting for more data to be available before it can actually continue processing. So bandwidth has to be increased as we have more um, nodes available. The other thing is that bandwidth can be increased by improving the the networking technology. So if you have more interconnection and better networking technology for the interconnection, then the bandwidth can be increased. But there is one limiting factor in this, and that is actually the other factor, latency or the delay. However, latency is a function of how fast you can transmit the signal. So there's no way that you can reduce the latency if the size of the computer is, let's say, a few hundred meters, because it is determined by the speed of light, which is a universal invariant according to Einstein, right? The laws of physics does not allow the speed of light to increase uh, with your network. So you are basically going to be limited by the size of your network, and there's no way that you can actually overcome the latency unless you could shrink the dimension of the HPC or the supercomputer. So one approach that people have been trying out to overcome the latency is to actually put all the CPUs not on multiple distributed computers but within the wafers. That means you shrink the size of the supercomputer into a series of wafers, which typically are used normally cut up into multiple CPUs, but now we keep all of them within the same wafer, so the dimension is actually reduced. So that way is one of the ways that we can overcome the problem of latency. But with current designs of supercomputers, instead of using the wafer scale computer, we can overcome the bandwidth, and we're going to take a look at some of the common ways that people have done this over the last couple of decades. And But latency can't be reduced, right, just by using better networking technology. So there's a survey by Lu and Ming and Jun Sheng, and this basically tells us some of the common, and this is quite a recent article, tells us some of the common interconnects used by some of the fastest supercomputers in the world today. And you can find that actually in the top 10, the dominant one is actually InfiniBand, which is a standard, a non-proprietary kind of interconnection. So there are multiple vendors for InfiniBand. Then a big proportion is also using the Cray, and surprisingly, custom interconnects is actually taking up like 30% of the overall pool out of the top 10. When we look at the top 500, the situation is still the same. The top 100 is basically dominated by InfiniBand, the light blue one, then Cray, right, and OmniPath. They take up a significant portion. Then you can see that the custom, they grow from a significant portion of about 10% for the top 100, but it tapers off. And then we see others like Ethernet, right? Both the 10 gig and the 25 gig versions emerging for the vast supercomputers, but they are not within the top 100. Okay, so these are more commodity-based technology and much cheaper and much more affordable, but the top end computers they are still using mainly InfiniBand, Cray, and then others, the custom ones. So let's take a look at some of these common ones for the top 10. Number one, this is a table to just give you the details of the top 10 uh, supercomputers and what is the kind of technology being used. I'm sorry, the top 50, I think. So first is InfiniBand, which is basically a switch-based system, and there's a hierarchy of switches that can support this. It is basically enables them to basically transfer the data very, very quickly. As I said before, InfiniBand is one of the commonly used ones for the top 10 supercomputers. Then we have the OmniPath, which is also based on switches, but you can see that the levels may not be as many levels as what we see in InfiniBand, but it is possible to have additional switches and links in OmniPath. Then we're going to take a look at one of the proprietary ones from Cray, which is based on the slingshot technology. And they have also got a custom crossbar switch called the Rosetta switch that basically switches the data from port to port. Okay, so this is the Cray one, which is again one of the commonly used one for the top 10 supercomputers. Then we're going to take a look at what Fugaku is using, which is a proprietary, a custom interconnect called Tofu. So again, they have a crossbar switch, but they have their own custom controller, Tofu network interface, or TNI, that's connected. And so this is basically one single node, right? We have the common memory core, three common memory groups connected to some sort of switch infrastructure, and the switch infrastructure consists of the TNI, the Tofu network interface, together with the router that can actually blast data across to other nodes through the custom Tofu interconnection. So here's some quick quiz for you. So just pause a while and try to answer the questions. If Amdahl's law predicts that 10 processors take 100 seconds, does it mean that 1,000 processors will take 1 second? That means, does it scale 100%, right, linearly to complete the same job? Is this true or false? And the second question, we have a large network of AI HPC nodes that use GPUs. Okay, so the nodes themselves have a GPU to accelerate the AI computations. Does this mean then, since we have GPU, we do not need to worry about the speed of the HPC interconnection? Is this true or false? So we have some references that you can take a look. The few that were mentioned earlier, the Gustafson's law, Amdahl's law, roofline model, as well as the article, that survey, and it's actually available online from MDPI. And with that, we come to the end of this section on AI HPC principles. Thank you for your attention.